Welcome to UVU CS3060, Lecture 1.6, where we talk a little bit about I/O devices and the persistence of data on those devices. So let's expand what we know about computer systems. Computer systems generally consist of the CPU, which we've already discussed in detail, and the main memory, again, which we've discussed considerably. But there are usually more devices than that. You definitely are going to need something such as a keyboard and mouse to allow for user input. You may have drives, storage devices that are managed, that are used to store data when the computer is turned off, as the data cannot reside in CPU and memory after power has been removed. In most cases, you'll also have a monitor, an output device, such as a monitor, and even possibly a printer. When we have concurrent access, and we've talked a little about this before, one or more CPU may try to concurrently access some of these devices, and an operating system should control those concurrent accesses. Well, this expands our von Neumann architecture a little bit more. Again, the CPU was used to execute instructions in a thread, and those instructions come from main memory, and usually those instructions modify data in memory as well. But now we add devices, and we may have one or more of these devices. Devices are communicated from the CPU to the device via I/O requests. These are commands that basically indicate what the device should accomplish. For example, on a hard drive, it may be an I/O request to read data from the disk. Most devices will have a certain amount of space, storage, memory space, where data can be transferred from the CPU to the device or read from the device. Most devices have a method also of sending indicators back to the CPU that something needs to be done. We call these interrupts. These interrupts cause the CPU to stop what it's doing and perform some operation to manage that particular device. There is an extra mechanism that some devices support where instead of having the CPU make requests, pull data, and send it to the memory, and keep doing that over and over again, instead of using the CPU in such a wasteful way, there is something called direct memory access, or DMA, where the CPU can send a command to the device saying, at this memory address, perform some operation, at which point the device communicates directly to memory using the system bus. Now, most devices have what is called a device controller. A device controller is what accepts the commands, contains the small data buffer, and then with this device controller can also send interrupts to the CPU when commands are complete or when action needs to be performed. For an operating system, there will be a special set of code that is used to manage that device called a device driver. And this device driver usually has several parts to it. It has an interface that makes device access uniform and easy. It also generally handles the interrupts that come in from a device using exactly what you think, an interrupt handler. So an operating system can be said to be interrupt driven if it manages these particular interrupts from devices. We've talked a little bit about hardware interrupts that comes from a device, but there are all other interrupts that come from the CPU, and we call these software interrupts. There's two kinds of software interrupts, we have an exception. An exception is where there's a software error. Say, for example, a division by 0. There are lots of different exceptions that a CPU must have handled by something other than the program that caused the exception. We also have an interrupt called a trap. This trap usually is used to request operating system services, such as reading and writing from a device, or asking for process management, whatever it may be. There are some systems that can send software interrupts for situations such as an infinite loop, or when you have processes that are modifying each other or the operating system. Those exceptions, there are lots of different exceptions that can be caused by software. So let's talk a little bit about what we do to save data. As hardware, especially memory and CPU, the memory for these particular devices are lost when the power's turned off, and we call this volatile memory. Volatile memory just simply means it won't last past the point where you turn off the power. Now, computers wouldn't be terribly useful if everything was volatile and we had to re-enter the data every single time. So we have persistent storage where data can be kept while the machine is turned off. Persistent storage includes things such as non-volatile memory, hard drives or hard disk drives, optical media, and magnetic tape. Now, all of these devices have various positives and negatives, various pros and cons. We'll talk about those in a moment. But the operating system needs to manage these devices so that we know which processes may be allowed to access a specific device, or perhaps are restricted from a particular device. One thing that also needs to be managed is what format do we save the data onto these persistent storage devices? Is there one format we want to use for all devices? We usually call these things file systems, which allows everybody to have a uniform access to a particular storage device. So you can save data to a file and then read from it later, either from the same program or from a different program. We really don't want to have different applications trying to save data to a persistent storage device that can't be read or understood by other programs. Now, storage devices have different performance levels. Here we have a table that demonstrates how the different data storage areas, their sizes, how fast they access. Something to realize is as we go from level to level, the actual cost of using a particular storage goes down significantly. Registers tend to be very expensive, and there are very few of these on each CPU. Typically, they're less than a kilobyte worth of data. Sometimes we can even consider them in the tens or dozens of bytes. Registers are almost always built directly onto the chip and are very fast. Storing data inside of a register is primarily what a CPU instruction is trying to do. So you can take care of the registers very quickly from an instruction. Most access to registers is done after a program is compiled. Cache memory is not nearly as fast. It has a slightly higher access time, but there is more of it. And this is just a small amount of memory that is kept on the CPU chip so that the access to data can be a little bit quicker. In most cases, cache memory is not explicitly modified by software. This is something that's controlled by the hardware using cache managers and such. And so this is an implicit data storage area where when a CPU requests a piece of data, that data is moved from main memory into cache so that it can be quickly accessed on second and subsequent accesses. The next level up is main memory, and there can be quite a bit of this. Most cases, the operating system is the one that takes care of main memory, considering it a device that's on the bus, and we've talked about how processes have virtualized memory. The next level up is, of course, persistent memory. So solid-state disks is the start of that. From level 4 and higher, now we have non-volatile storage. Levels 1, 2, and 3, all of this is volatile storage and will go away when the system power is removed. But solid-state disk is very quick, but not nearly as quick as the other levels, the lower levels that we have. It is treated a lot like a disk, and in almost every case, a solid-state disk is going to be managed by the operating system. And finally, we have magnetic disk, where we can have a lot of storage, but it is really slow. Its access time is in the 5 millions of nanoseconds. So we're talking easily the millisecond range here. And so, while magnetic disk can store quite a bit, it is slower, and thus it is better utilized when the data on the disk is cached by lower levels, either moved into main memory or in cache or stored into a register. Now, magnetic media can include disk or tape. So there's lots of different options when it comes to magnetic disk. Slower, but definitely much higher capacity. So what is this caching I keep talking about? Well, in these environments, we want to make sure that data on slow media is kept in faster storage areas. So maybe data in hard disk gets loaded into main memory. When the CPU accesses data from main memory, a copy of it is stored in the cache so that faster access can be made, and that the hardware registers is the ultimate end-all. But we have a problem here, especially in multiprocessor environments. We have an issue where sometimes these caches can become out of sync with other caches. So say we have two processors, each working on the same data in memory. Those two processes one process could modify data in main memory, but the second process may not know about that modification and use old expired data within the cache. Well, in a multiprocessor environment, it is important to provide cache coherency. Cache coherency is where everybody's caches, every processor's cache data is actually synchronized with other caches. It becomes even more complex when we work in distributed environments where we're actually working with different memories and even different storage areas. And how we actually manage the coherency between those caches becomes critical. That does kind of go a little bit beyond the scope of this class when we talk about distributed systems. But it is worth understanding that cache coherency is an issue that extends well beyond just a simple machine. So, what's available for us to help persist our data? Well, some simple ones are system calls that are provided by the operating system that allow us to do things like open files and read from or write to those files. Again, we talked a little bit about system calls, how they transition to a privileged mode. And frequently these system calls actually don't write directly to a device, but rather format the data so that when it's written to the device, it can be read using a format. And we're talking about things like file systems, where the data is organized in files and directories. How is that organization managed? Well, that's why we have file systems that allow us to control how that data is stored onto a particular device. Now, these system calls usually are fairly basic. So if I choose to write data to a file, I specifically have to tell it what bytes to write and how many of those bytes there are. There are other particular APIs that an operating system usually comes with, which reside not in the operating system kernel, but actually come as user space libraries. These are libraries that your program can use to help you accomplish some higher level tasks. For example, we've been using the printf to format the data we want to display on the screen. The printf is a function within a user space library. And there are lots of different formatted I/O, and we've seen some threading calls in the thread demo. And most of this is actually managed in user space using a special piece of code that is not necessarily directly executed, but is available for our executable files to call as functions. A lot of these libraries are actually part of the operating system. The operating system will ship from the vendor with these libraries to be made available to program vendors, application vendors, and to you as a developer. So at this time, if you transition over to the demo where I show how to manipulate data on a persistent storage device.